Who am I? I'm Alexis Gallagher. I've been an independent iOS developer for a long time. I actually recently joined a fashion tech startup, so if anyone else here is interested in augmented reality, custom manufacture, and fashion, please reach out to me. I'll tell you about that. But right now, what I'm talking about is value semantics. Now, I don't know if you all remember, but I feel like 2015, 2014 also, a bit of 2016, I think of these as the bumper crop years for talks on value types, right? There were at least like half a dozen talks on value types. Apple's done, I think, 3 of them, if you count the last WWDC. There was a really good one here by Andy Matuszczak and a couple other ones. So why do we need another talk on value types? Fair question. I'll give you sort of 2 reasons. One thing I noticed in almost all the value type talks, especially the ones that got into more advanced material, is about midway they'd use the phrase value semantics. And then they'd never define it. And then they'd sort of keep marching. So it was sort of stuck in my mind as this puzzle, like what is this thing that they need to keep bringing up, but it's never really explained what it is. And I also found that the term value semantics often came up around the point where those talks got really complicated. Like they'd start by saying, hey, value types, relax, you know what they are. It's like integers. You've always dealt with integers. Here you save an integer. Here you check an integer. And it's like, great, value types. I'm rocking it. I understand this. And then like in the middle, they're like, and this is the copy on write optimization to get at deep storage. And like by then, it just seems like it's a much harder talk. And around that point was when value semantics would pop up and then disappear like a monster, like jumping out from behind a tree at night and then like hiding again. So I formed the idea in my mind that these things were connected, and that if I understood value semantics, I'd also understood why all these talks got complicated at the same point. And I think that's actually true. I think understanding value semantics in a clear way helps you understand value types much better and gives you a much cleaner frame for understanding everything connected to value types. And value types are important, right? Because they're updating foundation to use them everywhere. So it's no longer a sort of minor quirk of the Swift language. It's part of understanding foundation. It's part of understanding the core types that we use to build all kinds of apps. So that's why I think value semantics is worth getting into, even though it's only mentioned in passing. I think it's the thing that's been in the center of the room that we haven't pinned down, but if you pin it down, other stuff just falls into focus. So now to maybe illustrate that I feel like it's not pinned down, I'm going to have a pop survey. And I swear in the beginning there are no wrong answers here because almost every possible answer is right according to someone's perspective. So quick survey, and you guys are the diehards who are still here, so I know you're going to raise your hands or not. Would you say who here would say that all structs are value types? Are structs value types? Are all of them value types? Okay, so it's about like 65% of the room tentative. What about all classes? Are all classes value types? If I define something with class, is it a value type? No. Okay. So you're saying no, it's a reference type. All right. Now, what about do all structs have value semantics? I've got a firm yes in the middle. Let's see how many people are just not answering. Who here says all structs don't have value semantics? I got one other person. So one person says yes. One person says no. And for everyone who's watching from the camera, about 58 people have not raised a hand at all. So value semantics is a bit ambiguous. Next question would be, do classes have value semantics? I think we'd get the same kind of answer. Value semantics is not very frequently defined. And when you actually dig into the literature, all sorts of answers are viable. So my agenda for this talk is first I want to review value type stuff that we've encountered before, but also get into value semantics in the context of that review. And then I want to propose a definition for value semantics that I hope makes it something you can kind of grab and use and really understand. And last, I'm going to offer a recipe. If you want to define your own type and you want to be sure it has value semantics, here is a checklist-style recipe for doing it so you know that you've got a value semantic type. So first, let me review it. And I think the easiest way to start getting into value types and value semantics is not with an abstract definition, but it's with a game. And I've invented this game and I call it the mutation game. So the mutation game is played with 2 players. We got Victor the valuecist. He's a good guy. And then the bad guy is Salazar the side effector. Right? He's the bad guy. And the game is this. Victor the valuecist is going to choose a type foo. He's going to set a variable of foo with a value. And then Salazar is going to try to attack that variable. He's going to try to change the value of that variable. But here's the trick. Salazar doesn't get to touch the variable. All he gets to use is another variable, s. That's Salazar's attack variable. Salazar also gets to define a pure audit function that's used to measure the value of v. It needs to be a pure function. You can't just like pull in a random variable. And here's the arena of play, right? So this should look pretty similar from talks we've seen on value types. So in the beginning, the valueSyst Victor defines the variable v. It's of type foo. And then we get this important statement in the middle, var s equals v. So now so the value of s has now been determined by the value of v. And we take the initial value of v with the value of function, and we're just going to save that into v0. And in that blocked out comment, that's where Salazar can do anything he wants to do, as long as he's only using the variable s. He can't touch the original v. And then we take the value of v again, and we see, has it changed? Or is it unchanged? If it hasn't changed, then Victor wins. If it has changed, then Salazar wins. Now, I'm not going to lie to you. This talk is a little bit abstract. I'm talking about value semantics versus value type. So to try to liven it up, I've tried to make this concrete. And so these are the two characters, right? There's Victor the valueSyst, sort of hero of like virtue. He looks like he's probably marrying someone who I just cut off the frame, so you only see her hand kind of grabbing his arm. But he's a good guy. And then there's Salazar the side effector. He's much more dramatically dressed, sort of seductive, but evil. Right? So he's tempting us, but we shouldn't be tempted by Salazar the side effector. Thank you, Alan Rickman. God bless. So let's play out the game a few times. Like, what happens if Victor the valueSyst decides to play with the type int? Right? If Victor plays with int, then the valueSyst wins. You can't touch it. S cannot touch the value of v. Why? Because int is a value type, right? And what does that mean? When we say something is a value type or a reference type, in the context of Swift, really the thing that we're talking about is what I call assignment behavior. It means what happens when you assign to the variable. And this is the magic picture that makes the assignment behavior of value types, I think, very clear. Value types use assign by copy. So we start with a declaration that v, there's the variable, the sort of set of all variables there, is pointing to a particular instance, and that instance has a value. The instance has the value of 100. And then when we assign to a new variable s, assign by copy means it behaves as if we are creating a copy of the instance. That's why we have two instance boxes in this second row here. And the new variable s is pointing to the new instance, which was copied from the first one. But that new instance, maybe because it's made of the same bytes, it points to the same value. It also points to 100. So whatever happens later, whatever Salazar does with s, it's only going to affect that instance that the variable s is pointing to. It can't do anything that changes the value of v. The value of v you get by taking the variable v, going to the instance that it points to, and then looking at the value that that instance carries. This is a way to think about assign by copy, and this is why for a type like int, the valueSyst always wins. But what if Victor is relaxed and naive and trusting after his wedding day, and he goes with NS mutable string? Well, then he's totally hosed, because this is a reference type, and reference types use assign by reference. So as you can see right here, looking at the same kind of diagram, the variable v points to the instance, the actual mutable string thing, and the value of that mutable string, it starts out as, what have I got there? An empty string. And when you go var s equals v, what you're really saying is I want to have a new variable, and I want it to point to the same instance. So v and s now share a common instance. And then what can happen is that if someone makes a change to the actual instance by, say, by mutating that mutable string and filling it with hello, so that its value is now hello, well, now the value of v is hello, and so is the value of s. So Salazar, just by grabbing hold of s and using it as its handle, is able to get in there and destroy v, destroy what it was supposed to mean for us. So what, right? So what's the big deal here? This is probably retread of familiar material, but this gets at the benefits of value types. Value types prevent unintended mutation. If I don't want to worry about v getting messed up, and v is a value type like int, for instance, then I don't need to worry about someone who's holding on to S doing something that messes up V. So that's good. Why is that good? It makes it easier to reason about what you're doing. You just look at what happened to V. You don't need to look at something else that might have this like indirect spooky effect on V. Makes it easier to reason locally, meaning just look at a little bit of code. Makes functions great again is another way to think about it, right? So if I have a function and it takes an int and it returns an int and it's a well-behaved function, I don't need to worry that under the hood it's doing something to the int that I handed into it, because the rule for the variable that's used in the body of the function is the same kind of assignment rule that's used for assigning a variable within a block of within a scope of code. And all of this also helps with thread safety, again, because you don't have to worry about something else changing something that you didn't expect and possibly in the wrong order. So far, so familiar. There have been a lot of great talks on value types. Here's like a short list of them. But this is the sort of easy part of the value type talks before they start getting a bit tricky. What else what else is there to say? Should we always just use structs when we want to have this safety, and then we can use classes when this kind of safety isn't important to us? Is that as simple as you'd want it to be? Not exactly, because what I've described as a benefit of value type is not a benefit you always get from a value type. So saying it's the benefit of the value type is a bit misleading. Because, for instance, one way I can get this benefit is by using a reference type that happens to be immutable. Right? So look at what happens with UI image. Right? UI image, I define a UI image here that represents a smile. Let's look at it with the pictures. I defined a UI image that represents, say, adorable children holding pumpkins. And then I define a new variable, S, that's pointing at the same instance. And now we might worry that Salazar could grab S and then do things that would change the image. Right? He could go change the colors on it or something. But actually, you can't do that, because UI image has been deliberately, carefully defined to be immutable. If you look at all the properties on UI image, they're all read-only. There's no function you can call on UI image that's going to change the image inside it. There's no property you can set on UI image that's going to change the image itself. And as a result, even though these variables, at the instance level are sharing content, they're sharing the same instance, it behaves as if they're totally separate, because you can't change one from the other place. So this seems to be one of the benefits of value types, right? That I don't need to worry about Salazar. But this benefit is actually for a reference type, because that reference type is immutable. Well, okay, you might think. So maybe some reference types have this benefit, but value types, I can still go with a value type if I want to be safe. Not really, because I could create a value type, like array, that contains inside it a reference type, like an NS-mutable string. So in that case, we still have this problem. I've got a value type V. I assign V to S. I take the value of it. But now, within the array, I can go in there and grab the first instance, which happens to be mutable, and change that. And now, if you take the big picture, the value has changed, because the value should be defined by everything that's contained within it. If you want to look at the picture of it, it looks a bit like that. The variable V is pointing to that first box, which is the array. And that array instance is pointing to the second box, which is the mutable string. And when I go var s equals v, yeah, okay, I'm copying to create a new array, but that new array instance is pointing to the same mutable string. So I have exactly the same problems as before. So this thing that you might think of as like the benefit of value types, well, sometimes I get that benefit with a reference type, and sometimes I don't get that benefit with a value type. A bit puzzling. And it's not just for arrays. Really, it's for any value type. So here's the same thing with a struct. If I define a struct and it has internally a property that is a reference type, you get exactly the same issue as you'd see with an array. These are called, sometimes called nested types, and the rule that defines them is messy. Now, Apple themselves in their talks about this problem as they're getting into the benefits of value types. They describe it as unintended sharing. And it's not always unintended. This is where the talks start to get complicated. Sometimes you want to do this because you want to sort of secretly maintain common storage for efficiency reasons. But then you don't want that secretly maintained common shared storage to mess up the behavior of your types. So you put in special tricks to be sure that as soon as you would change something that's shared, then you stop sharing it at the last minute. This is the copy on write optimization. And they go into this in the 2015 talk. And it's a great talk. It's worth looking into. But coming back to the big question here about the benefits we're trying to reach, and if we're the value syst and we want to know what kind of type can I use if I want to win the mutation game, we need an answer for that. And the answer is not value types, because clearly a nested type fails. And the answer is not avoid reference types, because sometimes a reference type works. What is the thing that wins the mutation game? So this is actually the definition of value semantics. The kind of type that wins the mutation game is a type that has value semantics. And something like int has value semantics, but you can also make more complicated things that has value semantics. But what we're talking about when we talk about these benefits is whether a type has value semantics. We're not talking about whether it's a value type. So having set that up to try to talk about what I'm getting at, let me define it. And the reason I think it's good to have a definition is because the many talks on this issue, the thing I found confusing about them is they'd kind of start by saying a value type, well, it's like int, right? And then when they got to the part where they started talking about copy on write optimization and this like deep storage issue, they'd say like, well, we want it to behave like a value type. But actually they were talking about a value type that they're trying to make behave like a value type. So that's not a good definition. So what's the definition I'm offering? My definition, here's an operational one. The mutation game is the defining test of value semantics. Simple as that. So I would say a type foo has value semantics if the value syst will always win the mutation game. The thing I like about this is it's very easy to think about because it's sort of adversarial. If someone gives you a type, you can just imagine code like this and think, well, is there anything I could do that would mess it up? It's not too abstract. But let's say you want a kind of abstract statement of it. I think that's good for getting at the essence of what the benefit is here. Here's a conceptual definition which amounts to the same thing. Value semantics amounts to being a guarantee of the independence of the value of variables. And independence doesn't mean structural things. What we're talking about is, can one thing affect another? Does one thing depend on another? So a type has value semantics if the only way to modify a variable's value, a variable that has that type, it has a value semantic type, is through the variable itself. If the only way to modify a variable's value is through the variable itself, then congratulations, you have a variable that has a value semantic type with the kind of parenthetical proviso, where we understand that when we talk about a variable's value, what we mean is the value of the instance the variable refers to. I'd say, strictly speaking, it's clearer to say that only instances have values and variables are just referring to instances. And what is the value of an instance? It's the thing that you're trying to compare when you define equatable. Would be a short way to define it. I think this is a great property. I would love it if when I went and looked at documentation that Apple provides, that anyone else provided for a type, it would say, at value semantic. Because this is what you want to know when you're about to use a type. What can I rely on in terms of its behavior? Is it a value semantic type or not? Whether it's a value type or a reference type is really an implementation issue. This is the thing that matters from the point of view of the user, I would argue. And I'd say this definition is not completely crazy. I'm really adapting hints or unpursued angles that are in Apple's own definition. At one point in the talk that talks most about this, which I think the 2015 talk with Doug Greger and Bill Dudney, they describe it in a few different ways. One thing they say is variables are logically distinct. I don't like that really because variables are always logically distinct. They're like different names. I think what they're maybe trying to get at there is structurally distinct, but they're not actually saying the variables are structurally distinct. They're saying something about the storage for them is structurally distinct. But that's also not what matters, right? Because again, like you have immutable things where they're not structurally distinct. It's the same thing under the hood. What really matters is can one thing affect another, right? And they're kind of hinting at that where they say mutating one variable of some value type will never affect a different variable. Well, first of all, as they say it there, it's false, right? Because we've seen an array, a struct. If you have a nested type, then mutating one variable of a value type will affect the other one. And also, the important thing is not whether your variable can affect something else. The important thing is whether you are immune to being affected by other things. So I'd say that the formulation they have there in the middle is about right, but I would offer a kind of modest amendment, which is just mutating one variable will never affect a different variable of a value semantic type. That's what we're trying to get at here. A type is value semantic if it's immune from side effects produced by other things, not if it's guaranteed not to perpetrate side effects on other things. So I think this is the right thing to focus on when you think about what value semantics should mean. And I think the definition I'm offering is consistent with what everyone else has said, but I like the way it focuses things a little more. Or just a big summary of it, value semantics is about interface, whereas value type versus reference type is about implementation, right? Because again, value semantics is what you want to know if I give you a type and you want to know how it's safe to use it, whereas whether it's value type or reference type is really this detail about what's happening with memory under the hood. And I suggest we try to rise up to a higher plane when we can afford to, in terms of performance and other engineering restrictions. And to put this a bit more grandly, I'd say the value of value semantics is value semantics let you dream in values. They provide a simpler way to think about it. And let me offer an illustration of what I mean by that. So far, all of the charts I've offered have 3 columns, and they depict the relationship between variables, instances, and values. And this is the way you need to think when you're dealing with things that don't have value semantics. You look at these variables and you need to have a kind of model in your mind of all the little bits and pieces that they touch, and if a thing that was touched by many things got touched and got changed. The whole benefit of value semantics is that it allows you to forget instances exist. Because our definition of value semantics doesn't actually have the concept of an instance or the concept of reference in it. It only has the concept of variable and value. A type has value semantics, or a variable has value semantics if the only way to affect the value of that variable is through that variable. There's a whole concept of reference instance is gone. Because when you have value semantics, you can just use this as your mental model. I have a variable, and it has a value. And values don't change. They're sort of immutable, perfect, ideal things, if you think of them in the mind of God. And variables are names for them. It's a much clearer way to think about it, I think. And part of the difficulty, I think, part of the reason I think it's not often framed this way is because if you actually look at the word value, it's used in very different ways in computer science, especially if you look at the way the word value is used in sort of C++ derived languages, and Swift is really like that in the way a lot of the terminology works in the documentation, and the way value is used in functional programming languages, so languages like Clojure or SML or OCaml. If I had to characterize it, I would say that this sort of the C and C++ derived languages have a machine-oriented view of value. If you go digging through the C++ spec to find out where they define the word value, you go through footnote, 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 and then you find a footnote saying, we mean what it means in the C spec. And then you go to the C spec and you go dig, 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 and that also bottoms out in a footnote. And the final definition is value is the meaning that's attributed to an area of storage. But you see that the idea of storage is still what's at the bottom. And it's weird that these documents, the C and C++ language specs, that are full of kind of lovingly detailed intricacy about the nature of storage and bytes, at the end they just kind of wave their hand and say, it's the meaning you attribute to it. It's like they kind of like ran out of steam when they were trying to explain it. Whereas if you look at the way value is used in more mathematically derived or functional-oriented languages, it's much more value is like the number 5. It's a kind of mathematical, ideal, abstract object. And this is also why I'm avoiding the term pass-by value, which I think we've all encountered in programming language textbooks. Because pass-by value doesn't say what sense of the word value you mean, and then it gets totally complicated because you'll have like a reference pointer and say, well, it's pass-by value, but the value is actually a reference. The whole beauty of Swift and more abstract languages is that they hide the raw mechanics of pointer reference from you. So I think using terms like pass-by values is dragging us back into a more confusing representation that we should only work in when you need to be working at that level of representation. And all the benefits of values that people are pitching, where they talk about immunity from side effects and independence and easy to reason about, these are the benefits of logical values. These are not the benefits of value as an abstractly defined meaning around storage. There's a great talk by Rich Hickey, the author of the Clojure programming language, called The Value of Values. I highly recommend everyone go out and see it and watch it a few times. It takes a while. I feel like, just like my old English teacher would read Moby Dick every year. I feel like every year I watch it again, and then I understand more subtleties in it. But I think there's a lot of these benefits that actually come from the mathematical clarity of that kind of notion of value. So I've offered my slightly adventurous, but I would argue totally consistent with everything that's come before, definition of value semantics. Here are some consequences of it. So I would say, I'm putting my flag here into the ground, immutable reference types have value semantics. Boo. Gotcha, right? Okay. Come at me. I think this makes sense by any reasonable definition of value semantics. Yes, they're reference types, but they have value semantics in the sense that they behave like values and someone else can't mess them up. Second thing, if you think about it, types have value semantics not as an absolute matter, but only relative to an access level. Why? Because a variable has value semantics if the only way to modify the value of the variable is through that variable. Well, what you can do to the value of a variable from that variable depends on where you're sitting, depends on your access level. So if a type has a file private access modifier on something related to the type, then I can access it if I'm running code that was defined in the same file. But if it's not file private, then I can't access it from outside the same file. So if you think about it, what that means is that the type has value, might have value semantics from one access level, but not from another, because from one access level you can't mess it up, from another access level you can. And this is really already implicit in the copy on write optimization example that Apple uses and that everyone uses where they're talking about more elaborate types that want to maintain value semantics while also having shared deep storage. Right? They're using the access level here to control it. So if I could get in there and mess with the private var, the underscore path property, well then I would be spoiling the value semantics of it. So that's another thing to think about, that the types have value semantics relative to an access level. Now, that's some kind of summary on what are the consequences of value semantics, and I hope this definition is one that you can grab. I'd now like to point out how a nice thing about this definition is it offers you a fairly simple recipe. If you're defining a type and you want to ensure it has value semantics, let's say you're hacking on the uncompleted implementation of Foundation and you want to have a value semantic type. You need a recipe for it. You need rules you can sort of apply when it's like 11 o'clock and you're a bit tired. So here's my recipe for value semantic types. So let's say you're working on a primitive value type, like int. In that case, sit tight, you're done. Those types all have value semantics by default. Let's say you're working on a reference type, so something that's defined using class, which uses assigned by reference as its assignment behavior. In that case, make it immutable. If it's immutable, it'll have value semantics. How do you make it immutable? You use let constant properties. So you use so all your stored properties need to be let constants, and those properties themselves need to have value semantic types. So you can see how this. One of the reasons I think this concept is coherent is it recurses in this way that gives you a nice structure. Now let's say you're dealing with a complicated case of composite value type. Well, in that case you have a choice to make. So if I have like a struct, either use stored properties that all themselves have value semantic types, right? So if I have a struct, then and all of its properties have value semantic types, then I'm done. The struct has also a value semantic type. Or if I want to do this complicated thing with shared deep storage, then you need to handle the tricky copy on write case in the way that's been described. And just to sort of spell out the instructions on how to do the copy on write case, because I think people show examples, but they don't have to break it down. You can nail down what you're doing. Pick the value semantic access level for the type's user. Might be public, might be module, depends what you're doing. Restrict any mutable reference type properties to a lower access level. And then define accessible setters and mutating functions to copy the mutable instance instead of mutating a shared instance. And if you want to know if you've done it right, you can always just go and think about the mutation game test. Can Salazar like mess this thing up? If you can, then I haven't quite finished my job. You might even be able to automate this. I don't know. You probably can't. That might not be legible on the screen, but you can just define a flowchart, which is the questions you'd ask yourself to determine if the type you're looking at is a value semantic type by going through the recipe steps that you'd provide. To some extent, this might even be determinable through automated analysis of types. I think that would be quite handy. So to loop back and consider those questions that I asked, because there's a lot of ambiguity in the way people use this language, it really is true that you could answer a lot of those questions almost any way. But here is one consistent set of answers, one consistent interpretation. Are structs value types? Yes, by definition, because they use assign by copy. Do structs have value semantics? In general, no. But yes, when they're designed to pass the mutation game test. There's a couple ways you can do that. Are classes value types? No, by definition, because they use assign by reference. Do classes have value semantics? In general, no. But yes, when they are immutable. And there's a definition of how you make a type immutable. So the key points, if I would want to sum all this up, is what is value semantics? It means that only a variable can affect that variable's value. There's no other way to get at a variable's value. How do you test it? You can test it with the mutation game. Value semantic types can be built by this sort of recipe in a fairly straightforward way. And you can build them from value types or from reference types. Don't let people lie to you about that. The world is more complicated. But here, it's simple. Hope I got it all right. And value semantics is defined relative to an access level. It's not an absolute property. And fundamentally, value semantics is about interface. Value semantics is what you should care about. If I give you a type and you need to use it, and I tell you it's a value semantic type, I've told you much more useful information than if I told you it's a value type or a reference type. That's my kind of summary of the key points on this, having thought about it a little bit. Also, I just wanted to acknowledge discussions I had with other people that helped me think about this and helped me make it more clear. And if what I've said here goes off the cliff and is not quite right, then that's definitely my fault, not theirs. But that's what I have to say about value semantics. I hope that makes some sense.
I think you touched on something earlier when you talked about immutability enhancing thread safety. Mm-hmm. And when I, listening to your talk and looking at these language features of Swift, we had an earlier talk where someone talked about using Swift as a server. Mm-hmm. So I don't know why, but I keep thinking of the Erlang virtual machine. Yes. And, immutability, what they've done with the Erlang virtual machine in the language is shown the superiority of immutability when it comes to handling massive numbers of concurrent connections reliably. So will Swift ever approach that? Probably not, but it could, it's compiled, it's really fast. Erlang's also compiled. But anyway, I just couldn't help thinking about Erlang, and I think you inadvertently touched on the superior nature of Erlang when it comes to doing concurrent, reliable servers because of the immutability, and I believe they have kind of a write-on-copy type of mechanism at play.
I think that there's definitely a connection here, and I'd say that the concept of value semantics is a little more inclusive than immutability. Immutability is one way you get it.
Sure.
But
with immutability, you're kind of guaranteed it.
Yeah, immutability, you're guaranteed it, and but there's still some kind of mutation that happens, and usually, like I'm very familiar with Clojure because I've used that for building and shipping systems. And in that language, the primitives that you're given tend to be immutable, and then there's very controlled mutation around how you refer to them. Swift also gives you this very controlled mutation, but it's concealed a little bit in the way it works when you make something mutating. I would say that I think the copy on write optimization is a performance optimization to maintain value semantics while under the hood, you're doing this stuff that keeps storage cheaper and makes copying cheaper. But the functional programming languages like Clojure, maybe like Erlang as well, I don't know.
Yeah.
They'll do much. Their copy and write is the first and most simple kind of optimization of that kind that you can do. There's this whole area called persistent data structures. There's a book by Okazaki. It's quite cool if you're interested in it. And you can build data structures that do much more elaborate and fine-grained kinds of structural sharing of the deep storage while maintaining an external value semantic interface. And actually, I think it would be great to implement those in Swift, and they would be useful on the server, and you would get very good performance with them. So I think it's something to do.
Well, Swift is potentially, it's like more of a general purpose language that can be mutated and manipulated these various ways like you've suggested. But I think with that one particular use case of having a massively concurrent, reliable server, I think that battle's been won by the Erlang virtual machine. So, because that's what they tuned it for, right? So
Yeah, it also has a error handling model that's very well
yeah,
thought
yeah,
out.
the
Other
supervisor and
things that are
restarting
good about
things,
it.
pretty cool. Yeah. Thank you. Great talk.
Thank you.
Where do you think this, is there a framework or something to be structured to help people get this better? Has anybody written any excellent structures or frameworks to use these things?
Well, I think that we're already using these things all the time.
Yeah, but I mean consciously in best practices. Because
No, and I
Yeah.
find that a bit puzzling, to be honest,
Yeah.
because I feel like I really do think value semantics is more important than value types, in that it's the thing that matters when you're deciding how you can use a type safely. Obviously, people have they have an excellent working understanding of it, because all of the people at Apple and elsewhere are very carefully building types that have these copy on write optimizations, while carefully maintaining value semantics. But then the term value semantics is very rarely used
yeah,
and not used consistently, even though that's the thing people are struggling to maintain and see the value of. So why don't we talk about it more?
yeah.
I don't know. I think it is partly because of this different ways of using the word value, and then people have this idea of like pass by value from like computer science class, and that idea just confuses them in the way they think about it. But I think fundamentally this is like a simple idea. All it means is if I have a variable, nothing can change it except using the variable. It's like so simple.
And we use
So why
this-
isn't it just put this way? Right? I don't know.
I'll
I
say
didn't see
why.
this anywhere. I just had to
I'll
make
tell
this
you
up.
why, and I'll say it here, because people who write software and who are addicted to the software, how shall I say this, sacred cow, don't want to use structures that come from web-based, server-based controls. And for read, write, CRUD, stuff like this is the variable controls we use for servers and the internet and things like Erlang to keep mobile networks up. That's why, like, for Python, you have like the Disco framework and these other frameworks that are built this way, structured for massively distributed systems where there is not safe, you're not sure stuff's going to stay up. And that's why, like, you have to open up the whole door to writing stuff not just like pure software. You have to write it like webware, which is built for stuff and systems to break. And it's a structural model. Like, that's what we were talking about. A listener, what was the other one?
You need to give this talk at WWDC.
Yeah, yeah.
They need to have you as their
Yeah.
methodologist at Apple.
Yeah, because you can speak software to them in a way they'll accept. I'm an ex-Apple guy. Like, now I was a Cisco
Well, we'll talk to
before
Tim
that.
Cook about that.
Yeah, so, yeah. But great presentation.
Thank you.
This is excellent.
I'm not sure if this is totally relevant because it goes into the implementation, but for mutating get, how exactly does that work? Because let's say some struct that I'm using has a NS mutable string, and
Right.
I use a regular get, and I have a hold on that NS mutable string, and then I try to mutate it. It's not going to go to the mutating get, is it? It's just going to, I already have access
Right.
to
So you're
0.
asking about the mutating get that you see in the
The
copy
UI
on
does
write
that.
optimization.
Yeah.
Yeah, so let's look at that. See, they do it here in a somewhat indirect way. Basically, the trick is, and here they're doing it by defining a kind of path for reading and path for writing, which I think obscures it. Basically, the trick is when you have, say, a function that is going to modify one of your shared mutable properties. So say I have a function foo, and I have a type foo, and I have a function in it like update counter, let's say. And then internally, I also have, let's say, an integer x. And that's the thing that I want to have shared until I can't afford to share it anymore. The update function gets marked as mutating, so the type system knows that it needs to treat this as a modification. And then in the body of your function update, you check to see if the stored property x that you're hiding is being referenced by more than one variable. And there's actually a function called isUniquelyReferenced. So you can actually just write conditional code in the updater that will check to see if it's being referenced by lots of people, by lots of other instances. And then, so, just to say, go back to one of these diagrams that shows a nested type, because that's what we're talking about. We're talking about a kind of deliberately nested type. Yeah. When you're doing this update, you can talk to the runtime that the language gives you and say, hey, wait a minute, is someone else also using this thing that I'm about to change? And if it says yes, then you just create your own copy of it. And if it says no, then you don't actually need to bother. So there's like special methods, which are basically have names like is uniquely referenced, which you can use to check at the point of access if you're about to change something that someone else is also changing, and then you kind of hide it the moment that happens, so no one can ever tell that they were being shared all along. Yeah, that's used for all of these types. So one analogy I think about is like, let's say you go to a store that sells stationery, and it has all these little shelves, and every shelf has a nice little notebook on it, you know, and they're all like the same because they're selling a lot of these notebooks. And then you like walk up to the shelf and you're about to reach for one and write on it. But secretly, the shopkeeper is like watching you, and the moment you grab it, the shopkeeper, faster than you can see, goes and like does this action. And what are they doing? Actually, you weren't seeing a bunch of different notebooks. The guy has like one notebook in the back, and then he has this system of mirrors. So everything that you thought was a distinct notebook was actually just a reflection of this one notebook. But the moment you're going to start writing on it, well, that's when his system's messed up. So before you can actually touch it, he like swoops in and puts a writable notebook in your hand. And that's the one that you grab, and then you write on it, and you're like, okay, great. And you never realize that all along, you know, you were lied to originally. And that's what copy on write optimization is. You've got all these distinct variables that behave as if they're pointing at distinct things, but actually it's all mirrors. There's just one thing under the hood. But as soon as you do something that would spoil that illusion by changing the one thing, because remember, if the shopkeeper didn't show up and I just wrote on that notebook, then I'd see my writing on all the reflections if that was the original, right? As soon as you're going to do something that changes it, then you do this quick swap, so the effect is not visible. That's the essence of the copy on write optimization.
So then when you make a type with copy on write, as like the maker of that type, you need to keep the cognitive load of like, oh, this is a reference or this is a value.
Exactly, yeah. As the person who writes the type, you have to bear the cognitive load of this like shell game you're doing under the hood. But the whole benefit of doing that is so that someone who uses the type doesn't even needs to know it works that way. And that's why value semantics is what's important. Because the promise you're making to the user is that this type has value semantics, and then they don't need to know if you're doing like funny business or not. Whereas if all you tell the person the type's a value type, well, that doesn't mean anything. It could be a value type that behaves like int, or it could be a value type that behaves like an array with mutable strings. So there's no, you know, that's not information that I can use. What I want to see on the documentation that annotates the type is, does it have value semantics? I don't really care, you know, about this implementation stuff unless I'm doing something that's performance sensitive where I actually need to know like how many bytes got moved around. And also, the Swift language is actually doing this copy on write thing under the hood all the time, even for the ints, which is why I sort of said in the beginning that value types behave, you know, assigned by copy behaves as if the instance is copied. Because that diagram I showed you in the beginning, just to sort of make the idea clear, this one, well, that's also a lie, because secretly the language at the runtime level might not be creating that copy until it needs to at the last possible moment. But you see how a talk that like ends up talking about copy on write can be confusing, because the real thing that matters is the value semantics which copy on write provides. It's like talking forever about an implementation and not talking about why you bothered with it, like what it's going to give you. Yeah, that's the whole point of the copy on write optimization, is it lets you have the benefit of value semantics from the outside while having the
flexibility and power of
well, having the reduced use of storage and the fewer copyings, and reduced use of compute for copying, you know, on the inside.
Awesome. Thank you. That made sense.
Thank you.
Great talk. I'm thinking sometimes protocols or you know, generic types that are part of the inheritance tree can be used to bring in behavior that such as this. Is that something that would be, do you have to, could you inherit this value semantics on types or even variables?
I'm not sure I know what you mean. So could you have value semantics as a property that you inherited from your supertype?
Or could you assign it like as a type? This is
Yeah, I don't know. I don't know. I need to think about that. I can't think about how you would do that off the top of my head, but there might be some way in which you could genericize the copy on write mechanism, because that is sort of generic, and then you could have specializations of a generic type where, like for instance, the example I gave of how you do a copy on write where the stored value or an int doesn't need to be an int, it could be a t. You know, it could be some generic type parameter that has constraints on it. So I suppose you could, you know, in that way have a value type where the kind of contents of it were generic. I haven't thought about that much though. This is an interesting question. I think we're all done? Thank you.